far beyond our world. 13. 8 billion years after the birth of the universe, the cosmos still unfolds its silent story. From the fiery birth of stars and the dance of distant galaxies, to the unseen threads of dark matter holding it all together, space is both vast and deeply mysterious. Astronomers have mapped billions of galaxies, traced the faint afterglow of the Big Bang, and listened to whispers of gravitational waves rippling through the fabric of space-time. Yet questions remain: what lies beyond the edge of the observable universe? Could parallel worlds drift just out of reach? And how do these infinite mysteries connect to the fragile beauty of our own existence? Tonight, we share the most relaxing and fascinating facts about the cosmos, guiding you gently into wonder, peace, and rest. Close your eyes. Let the journey begin. When we speak of the birth of stars, we begin with the nebula of the cosmos. These vast clouds of gas and dust stretch across hundreds of light years, silent and ethereal. Made mostly of hydrogen and helium, they drift in space like oceans without shores, their filaments glowing faintly when starlight brushes across them. Within these nebulae, gravity begins its patient work, pulling matter together, grain by grain, drop by drop, until dense knots form in the endless haze. Over millions of years, these knots grow heavier and hotter, becoming what astronomers call protostars. In time, nuclear fire will ignite and a star will shine. One of the most famous nurseries is the Orion Nebula, a place visible even with small telescopes, where thousands of stars are being born right now. Images captured reveal rivers of dust, glowing arcs, and radiant clusters hidden within its folds. To gaze upon it is to see the cradle of the universe, a reminder that every star in the sky once came from such a place of stillness that holds the promise of light. Yet mysteries remain in the heart of these clouds. Why do some nebulae give birth to stars while others remain silent fields of gas? The answer is not clear. And so astronomers search for signs, looking for hints of collapse or the faint glow of a forming core. Consider the Eagle Nebula, where immense pillars of dust rise like cathedrals in the dark, each one stretching 5 light-years tall. These are called the Pillars of Creation, a place where newborn stars hide inside cocoons of shadow. The view is majestic, like watching waves of a cosmic ocean frozen in time. Here light and darkness weave together, and specks of brightness pierce through the veil, showing the birth of suns that may one day warm planets and give rise to life. The process is slow, stretching across spans that human minds can barely imagine. Yet even within that stillness, the universe speaks. It whispers of creation, of cycles that repeat again and again, as stars emerge from clouds and return to them when they die. This is the rhythm of the cosmos, quiet yet eternal. Scientists have long wondered what begins this process of stellar birth. One idea is that a shock wave from a nearby supernova can pass through a nebula, pressing gas and dust together, sparking collapse where before there was only calm. Another view suggests that nebulae may form stars on their own when regions grow dense enough, without the need for an outside trigger. This debate continues, for evidence points in both directions, and the universe often allows more than one path to unfold. Imagine a night sky with fewer stars. Imagine galaxies dimmer and quieter. If supernova were not there to stir the clouds, could our own sun have been born in such a way, nudged into life by the death of another star? The thought is humbling, for it means that endings and beginnings are bound together, that even destruction can lead to creation. Perhaps this is the hidden order of the cosmos, a balance we are only starting to glimpse. Each new discovery opens another question. Each answer deepens the mystery. And in the heart of that mystery lies wonder. From the dense knots inside a nebula, a new stage begins. These knots grow warmer as gravity pulls gas inward, compressing it tighter and tighter. Slowly, a protostar is formed, hidden inside a cocoon of dust. At this stage, no fusion burns yet, but the pressure builds, as if the universe is holding its breath. Over time, the heat inside rises, glowing faintly in the infrared, a sign of the coming fire. Astronomers describe these objects as stars in waiting, seeds in the garden of the sky. In the 18th century, William Herschel observed hazy patches of light and called them shining fluid. Not yet knowing they were nurseries of stars, modern instruments have confirmed his vision, revealing protostars wrapped in veils of gas, growing quietly over millions of years. A single protostar may take 10 million years before it finally becomes a true star, a span beyond human imagination. To watch such a process is impossible in a single lifetime. Yet the cosmos holds it steady, as if time itself bends around these silent births. Each protostar is a promise, a flame that has not yet been lit, but waits with patience in the dark. Still, the mystery deepens. What decides whether a protostar becomes a giant blazing sun or a small faint star? The answer seems tied to mass, but the exact story remains hidden in the folds of space. Some protostars grow immense, gathering material until they weigh 100 times more than our sun. Others remain small, destined to glow faintly as red dwarfs. In the Carina Nebula, vast clouds give birth to some of the largest stars ever seen, giants whose light can carve through space for millions of years. To imagine these protostars is to see seeds scattered across a cosmic field, each one carrying a different destiny. They are like flowers in a garden, some blooming bright and brief, others quiet and enduring. For the observer, the signs are subtle, faint glimmers in the dust, soft flows of energy that whisper of a future star. In this uncertainty lies beauty, for the universe does not reveal its rules all at once. Instead, it lets us witness fragments, giving us glimpses of creation as though through a veil, inviting us to wonder and to wait. Scientists propose that the initial mass of gas collected in the protostar determines the kind of star it will become. More mass means higher gravity, greater pressure, and eventually a brighter and hotter star. Yet others argue that the surrounding environment matters just as much. The density of the nebula, the temperature of nearby clouds, even the radiation from neighboring stars may all shape the fate of a newborn sun. Perhaps both views hold truth, for the cosmos often works through many layers of influence at once. Imagine a protostar in a crowded nursery, surrounded by dozens of other forming stars, each one pulling with its own gravity, each one shaping the flow of dust. The path of that protostar may change entirely, growing larger or smaller depending on its neighbors. This raises deeper questions. If the environment had shifted even slightly, what kind of star would our sun have become? Would Earth still have formed around it? Would life have ever appeared? In the quiet of these questions, the cosmos hums, reminding us that our existence rests on fragile balances written in the earliest breaths of the stars. At last, the long preparation reaches a turning point. Inside the heart of the protostar, the pressure and temperature rise until hydrogen atoms are pressed so tightly together that they merge. This process is called nuclear fusion, where hydrogen becomes helium, and with each transformation, energy is released. Light begins to pour outward, and a star is born. The first glow is like a spark catching fire, and then it grows into a blaze that can last for billions of years. Astronomers using the Hubble Space Telescope have captured these moments, showing newborn stars peeking out of their dusty cradles. The brightness is astonishing, for a single young star can shine 1,000,000 times more than the sun when fusion begins. The energy pushes back the surrounding gas, carving clearings in the nebula, revealing clusters of glowing lights. To see these images is to witness the breath of the cosmos, the moment when darkness gives way to radiance. Each star in the sky has passed through this stage, each one a triumph of gravity and fire. The universe holds countless such flames, scattered across galaxies like lanterns in the night. Yet even here, mysteries remain. Some stars burst into brilliance almost at once, while others linger for ages before their fire begins. Why does the timing differ? The question leads astronomers to observe stars in transition, stars like those of the T Tauri type. These young suns flicker and flare, their light unsteady as if they are learning to breathe. Around them, disks of dust swirl, forming rings that may one day give birth to planets. The sight is delicate, like watching a flame tremble before it steadies. In these unstable years, the star reveals signs of its struggle. Sudden flashes, changes in brightness, jets of gas shooting into space. For those who study the heavens, such signals are like whispers from the newborn, telling us of the forces at play. And for those who simply gaze upward, these young stars are reminders of fragility, that even giants of light begin with uncertain steps. The cosmos shows us not only power but also vulnerability, and in that balance lies beauty. Every star that steadies into brilliance carries the memory of this fragile beginning, a story written in its first shimmering breath. Scientists suggest that the speed of rotation in a protostar may shape the exact moment when fusion begins. Faster spinning might delay the collapse, while slower spinning allows gravity to ignite the fire sooner. Others argue that magnetic fields play an even greater role, guiding the flow of gas, shaping the disk around the star, and perhaps deciding when the light will burst forth. The debate is ongoing, as observations continue to reveal both order and unpredictability in the heavens. Imagine if magnetic forces were weaker. Would stars shine earlier? Imagine if rotation dominated. Would the birth of suns be delayed across galaxies? These questions carry profound meaning, for the birth of stars sets the rhythm of the universe. Without their light, galaxies would remain dark. Planets would drift unseen. Life would never awaken. And so the arguments are not only scientific but also deeply human, for they touch on the roots of our existence. In the glow of every star, we see both certainty and mystery, both knowledge and wonder. Perhaps that is the lesson of the cosmos, that answers are born with questions, and that the light of the stars carries both. Stars do not all shine with the same light. Some glow red like embers. Their surface is around 3,000 degrees Celsius. Others radiate with a golden warmth, like our sun, burning at about 5,500 degrees. The hottest stars shine blue and white, reaching 20,000 degrees or more, their brilliance cutting through the dark with sharp intensity. The color is not only beauty but also a measure of temperature, a key that reveals the inner fire of each star. In the late 19th century, Annie Jump Cannon carefully studied the spectra of starlight, splitting it into bands of color and lines that mark the presence of elements. From this work, she built a classification system that arranged stars by their temperature and their light, a system still in use today across astronomy. Her insight turned the night sky into a coded library, where every star carries a signature of its heat and age. To look up and see red and blue and yellow scattered across the heavens is to see diversity written in fire. Each color tells a story. Each glow carries the mark of its nature, and together they weave the vast canvas of the cosmos. But the colors of stars do not always remain fixed. Some stars change, shifting their hues as their lives unfold. The question arises, why does a star alter its light? Why does it fade or brighten or turn from one shade to another? Betelgeuse, the great red star in Orion, gave a striking example in the year 2020. It dimmed so much that people across Earth noticed, wondering if it was about to explode into a supernova. Yet it later returned to its normal glow. Astronomers suggested dust clouds or changes deep within the star as possible causes, but the exact reason is still uncertain. To the eye, such stars appear like cosmic lanterns whose flames flicker, changing tone with time. Watching them is like watching a slow dance of color across centuries, a reminder that even the mightiest suns are not fixed, but living beings in the grand theater of space. Their light can be steady for ages, then shift suddenly, leaving us to wonder. Each change is a message, delicate and mysterious, that tells us stars are more than distant points of fire. They are evolving presences, shaping the beauty of the sky. Scientists propose that these shifts in color may come from changes in the fusion reactions within a star's core. As the balance of hydrogen and helium alters, so too does the energy released, and thus the hue we see. Others argue that dust drifting across the line of sight can veil a star, changing its brightness and apparent color without any change inside the star itself. The debate continues, for the universe rarely offers simple answers. Imagine if no star ever changed. If every light remained the same forever, we might think of the cosmos as static, unchanging, and our understanding would be far poorer. Instead, the sky is alive. Stars breathe and transform, their colors shifting as their stories unfold. If Betelgeuse does one day collapse and burst, the event will teach us more about stellar life than centuries of theory. Yet if it only flickers with dust, that too is a lesson about the fragile path of light through space. Each possibility is a door to deeper knowledge, and behind every change lies a truth waiting to be uncovered. In these mysteries, the cosmos invites us to keep watching, keep wondering, and keep learning. If the hidden language of starlight fascinates you, subscribe to Cosmic Sleep Science to keep exploring the universe with us. Every star has a life story. Written in fire and time, massive stars live fast, burning their fuel in only a few million years. Their brilliance short and fierce. Smaller stars like the Sun endure far longer, shining steadily for billions of years. The smallest, the red dwarfs, sip their fuel with such patience that they may live for trillions of years, far longer than the current age of the universe. Astronomers map these lives on the Hertzsprung-Russell diagram, a chart created in the 20th century that shows how stars change brightness and color through their existence. On this diagram, one can trace the journey of a star from youth to maturity to its final breath. The chart is like a diary of the cosmos, a record of stellar lives unfolding across time. It tells us that stars are not eternal but living entities, each one passing through stages of birth, growth, and decline. To see a star twinkle is to glimpse only a moment in that vast arc of time. Each star carries within it both vitality and impermanence, both fire and fragility. Yet the endings of stars remain among the deepest mysteries. Why do some conclude with a quiet fade into a white dwarf, while others end with the thunder of a supernova? Sirius, the brightest star in our night sky, offers a clue. It will end its life not with an explosion, but with a slow collapse, shrinking into a white dwarf within 2 billion years. Other stars of greater mass explode in fury, scattering heavy elements into space, seeding the birth of new stars and planets. The difference seems tied to mass, yet the details hold questions still unanswered. Observing dying stars reveals strange signals: sudden dimming, powerful flares, or changes in color that warn of endings near. To watch a star fade is to feel the breath of the universe, slow and inevitable. The cycle is like the breathing of the cosmos, inhaling with birth, exhaling with death, an eternal rhythm written in light. And we, standing on Earth, can only marvel, knowing our sun too has its place in this rhythm, a life that one day will find its close. Most astronomers agree that mass is the decisive factor in a star's final fate. A small star becomes a white dwarf. A medium star like the Sun will do the same. And a massive star ends as a neutron star or even a black hole. Yet there are debates about the role of companions. For many stars exist in pairs or clusters. Could the presence of a neighbor alter the destiny of a star? Might a star that should have died quietly instead explode because another star poured material onto it? The possibility is real, and such interactions complicate the simple rule of mass. Imagine if our sun had a twin pulling at it with gravity, feeding it with streams of matter. Would it still become a white dwarf? Or might it burn brighter? Perhaps even explode? These questions reveal how interconnected the cosmos may be, how the life of one star can be changed by another. Nothing exists alone in the universe, and even the fates of suns may depend on relationships unseen. The story of stars is not only one of fire within, but also of connections across space. When a star like the Sun exhausts its fuel, it sheds its outer layers into space and leaves behind a core. This remnant is called a white dwarf. Small yet incredibly dense, glowing faintly with the heat left from its long life. A white dwarf may be no larger than Earth, yet it holds the mass of a star. Its light is soft, a whisper compared to the roar of its former brilliance. The first white dwarf ever discovered was Sirius B, found in 1862 near the bright star Sirius. It was a strange sight, a faint companion to the most brilliant star in the sky. Astronomers soon realized what it meant, that stars do not last forever, but can leave behind these quiet embers. Though fusion has ceased, the heat lingers, and a white dwarf can shine for billions of years as it cools. It is a relic, a memory of a star's life, enduring long after the fire has gone. To see a white dwarf is to glimpse the persistence of the cosmos, where even death holds light. Still, questions remain about these remnants. Can a white dwarf ever reignite? Can it spark once more into brilliance? On its own, the answer seems no, for the fuel is gone, the fire extinguished. But when a white dwarf circles close to another star, gravity can draw material from its companion. As gas falls onto its surface, the dwarf may flare into sudden brightness, an event known as a nova. In these moments, a dead star glows again, briefly alive with borrowed fuel. Such events remind us that nothing in the cosmos is entirely isolated, that even the faintest remnant may awaken under the right conditions. To imagine a white dwarf is to think of a candle that has burned down, yet when touched with a spark may flicker once more. The light is fragile, temporary, but it speaks of the restless creativity of the universe. Even in endings, there are echoes of renewal. Even in silence, there are whispers of fire. White dwarfs hold this paradox, a death that is not entirely an end. The fate of white dwarfs is still a matter of debate. Some scientists believe that if a white dwarf gathers enough mass, more than what is called the Chandrasekhar limit, it could collapse into a neutron star or even trigger a supernova. Others suggest that without new fuel, most white dwarfs will simply cool and fade, becoming black dwarfs, dark and invisible, after trillions of years. But no black dwarf yet exists, for the universe is not old enough. Every white dwarf we see still glows, still carries the memory of heat. Imagine if one could return to fusion, if somehow the ashes of a star could blaze again. The cosmos would shift, for such rebirth would change the balance of light and darkness. Perhaps in the distant future, stars that we thought were gone may shine again. Or perhaps they will remain as silent witnesses, scattered across galaxies, unseen yet enduring. The truth is unknown, and that unknowing is part of their beauty. In their quiet persistence, white dwarfs remind us that endings are not always sudden, but can stretch across ages, fading gently into the vast night. When a star dies, it does not simply fade away. It gives back to the universe the very elements it created during its long life. A massive star that ends in a supernova scatters its layers into space, filling the cosmic ocean with carbon, oxygen, iron, and many other building blocks. Even smaller stars that end as white dwarfs release matter in quieter ways, shedding gas into surrounding space. This process of release is essential because without it, the universe would remain a cold sea of only hydrogen and helium. The Crab Nebula is one of the clearest reminders of this cycle. Nearly 1,000 years ago, in the year 1054, people on Earth saw a star explode so brightly that it could be observed in daylight. Today, the remains of that star still glow, spreading clouds of colorful gas and dust. Scientists can measure the elements there and trace them as they drift outward. The fact is both humbling and intimate. The calcium in our bones and the iron in our blood were born inside stars that lived long before our world even formed. Every part of us is touched by their distant light and final sacrifice. The journey of these elements raises questions that are still unanswered. When a star dies, its material is scattered with incredible force, traveling at speeds of millions of kilometers per hour. But how far can this matter truly go? Does it reach nearby nebulae? Or does it travel across galaxies? Carried by currents we can hardly imagine. Astronomers observe clouds of dust and gas drifting through space like tiny grains of sand in a vast ocean. Some condense near the site of the explosion, glowing in strange patterns of light. Others move far into the darkness, their journey measured in thousands of years. Imagine each atom of oxygen in our breath, once part of a star that burned and died in silence. The thought slows the mind and invites wonder. The stars are not just distant lights. They are travelers that leave pieces of themselves behind. The dust from one star may settle in another nebula, may join with gas, and may one day take part in the creation of a new world. The universe is a quiet network of giving and receiving, a slow and endless rhythm. Scientists have long debated what role this stardust plays in the cycles of creation. One hypothesis is that the heavy elements within the dust act as seeds. They cool the gas in large nebulae, allowing gravity to pull it together more easily. In this way, dust may help trigger the birth of new stars. Another idea is that stardust carries more than just simple matter. Some researchers wonder if within these grains there may be traces of ancient chemistry, the precursors of life itself. If that is true, then each explosion of a star is not only destructive, but also generous, scattering the ingredients for life across space. Yet there are disagreements. Some argue that the dust may simply remain inert, drifting endlessly without ever joining a new cycle. Others suggest it might preserve subtle records of the environments where it was created, holding information about stars long gone. The questions remain open, and they invite us to imagine what it would mean if stardust could speak. Would it tell us the story of stars that lived before our sun, or whisper about the worlds yet to be born? A supernova is among the most powerful events in the universe, the final act of a massive star that has reached the end of its life. When the core can no longer support the weight of the star, gravity wins and the collapse creates a violent release of energy. The brightness can surpass billions of suns, and for a brief time, the dying star may shine more than an entire galaxy. In 1987, astronomers witnessed a remarkable event, the explosion known as supernova 1987A. It was the closest supernova observed in centuries, allowing scientists to capture details of its unfolding. They watched rings of gas illuminated by the blast and traced the elements that spread outward. The power of this cosmic event reminds us of both destruction and renewal. The explosion tears apart the star, but the energy and material released enrich the cosmos. Without supernovae, the universe would lack many of the heavy elements necessary for planets and life. Each burst is therefore not only an end, but a gift, a flash of light that leaves behind seeds for the next generation of stars and worlds. Yet many mysteries remain about supernovae. Some stars collapse into neutron stars, tiny and dense, spinning rapidly and sending out rhythmic pulses of energy. Others collapse further into black holes, where not even light can escape. Why does one star leave behind a neutron star, while another forms a black hole? The answer is not yet certain. The Crab Nebula holds one such secret. Within its glowing filaments lies a pulsar, a neutron star that spins dozens of times each second. Astronomers record its steady beats like the ticking of a cosmic clock. Other remnants, however, show no such pulses. Only darkness that hints at a black hole. Each explosion is like a firework in the universe, dazzling and brief, but leaving different echoes. To watch these remnants is to see time slowed, to see the fingerprints of a star that lived and died. The sky holds silent records of these blasts, as if the cosmos has written its story in light and shadow. Each supernova reminds us of the balance between life and loss, between brightness and silence, between what is known and what is still hidden. Scientists believe the fate of a star after its explosion may depend on the mass of its core. A heavier core is more likely to collapse into a black hole, while a lighter core may stabilize as a neutron star. But this explanation may not be complete. Some argue that the environment around the star, such as surrounding gas or magnetic fields, could influence the result. Others suggest that subtle differences in rotation speed may play a role. These debates reflect how much remains unknown. The universe keeps its secrets slowly, offering only glimpses. There is also the larger question of how supernovae have shaped the universe itself. Without them, the cosmos would lack many of the elements that form worlds like Earth. Every rock, every ocean, every living being is touched by the ashes of ancient explosions. The thought is both comforting and profound. If supernovae had been different, if their processes had followed another path, perhaps the universe would hold fewer stars and fewer possibilities for life. It is a reminder that we are born not just from light, but from fire, from endings that became beginnings. The death of stars is not the end, but the start of something new. When the material of a star is thrown back into space, it does not vanish. Instead, it gathers, cools, and combines, forming new nebulae. From these nebulae, new stars and planets are born. It is a cosmic cycle of renewal, slow and patient, repeating over billions of years. Cassiopeia A is a striking example. It is the remnant of a supernova that contains more iron than 70,000 Earths. That iron is drifting outward, mixing with hydrogen and helium, feeding the birthplaces of future stars. In this way, the universe conserves and transforms its matter, turning endings into beginnings. Scientists estimate that as much as 90% of the material in the cosmos is recycled, used again and again through countless generations of stars. This rhythm is the heartbeat of the universe. It tells us that nothing is wasted. Every atom will one day find a new home, and the cycle of birth and death continues without pause. Still, the cycle raises profound questions. Will this process continue forever, or does it have an end? Astronomers study vast regions like the Tarantula Nebula, where the material from older stars has given rise to massive new suns. The sight is breathtaking. Clouds of gas shaped like delicate threads, glowing with newborn light. Each part of this process seems eternal, yet we know the universe is expanding. Will the stars continue to recycle matter as space grows colder and emptier? The mystery is heavy but soothing. To think of the universe breathing in cycles, like a tide that never stops, comforts the restless mind. The dust from one generation becomes the light of the next. The rhythm of this cycle is slow beyond measure, stretching across billions of years, yet it is steady, as reliable as the sunrise. In each twinkle of starlight, we see not just beauty but also history, the memory of countless lives before. Some scientists suggest that this recycling will continue as long as gravity can gather material, pulling clouds together to form stars. Others believe that one day the expansion of the universe will stretch everything too far apart, leaving matter isolated and unable to form again. Dark energy, the mysterious force that drives cosmic expansion, may be the deciding factor. Its influence is still uncertain, but it could eventually halt the great cycle of recycling. If that happens, the universe will grow cold and silent, with fewer new stars lighting the dark. For now, the cycle continues, weaving new stars and worlds from the dust of the old. The debate invites us to imagine what the far future holds. Would a universe without recycling be empty and quiet? Or would it find another way to create? For now, we rest in the knowledge that we are part of this great cycle. Our atoms will one day return to the stars, and from them, new forms will rise. The cosmos holds us gently within this eternal rhythm, reminding us that nothing truly ends, as the endless rhythm of stars reminds us that every ending is only a new beginning. Let your heart rest in this cosmic truth. Subscribe to Cosmic Sleep Science and continue this timeless journey into the universe together with us. When we look up at the night sky, we see stars scattered like dust across the dark canvas. Yet each point belongs to something larger. A city of light we call a galaxy. A galaxy is a collection of stars, gas, and dust bound together by gravity. Our home, the Milky Way, is only one among billions. Galaxies can take many shapes, but spiral galaxies are among the most striking. Their arms curl outward in sweeping arcs, forming patterns that feel both delicate and eternal. These arms are not solid structures. They are created by density waves that move through the galaxy, gathering stars like ripples on water. In the early 20th century, Edwin Hubble studied galaxies through telescopes and created the first system of classification. He revealed that the Milky Way is a spiral galaxy, a discovery that changed how we see our place in the universe. The Milky Way itself is immense. It contains between 100 and 400 billion stars. Each star could host planets, some perhaps with life. To imagine the Milky Way is to imagine a city so vast that no traveler could ever visit every street. Yet it is the city we belong to. The spiral arms of a galaxy glow softly in the dark. They resemble long, luminous pathways winding through a cosmic night. For billions of years, these arms seem to hold their shape, never dissolving into chaos. Yet this raises a question. How can such fragile-looking structures last for so long? Astronomers use powerful instruments to search for answers. The Gaia telescope has mapped the positions and motions of millions of stars in the Milky Way, tracing their orbits along the spiral arms. The data shows patterns, like invisible currents moving through the galaxy. We see the arms as streams of light, but they are also highways of energy and movement. The mystery is not solved, only deepened. The arms are both stable and shifting. They move slowly, almost imperceptibly, like gentle waves crossing an ocean too vast to comprehend. When we imagine them, we might picture roads made of starlight, each curve leading further into the depths of time. To lie back beneath the stars is to sense those arms above us, stretching far beyond sight, silent reminders that even in stillness the universe is always in motion. Scientists suggest that spiral arms survive because of density waves, patterns that ripple through the galaxy like waves on water. Stars move in and out of these waves, but the arms remain visible because the pattern itself persists. It is as if the arms are shadows of motion, not fixed objects but continuous echoes. Still, debates remain. Some believe that interactions with neighboring galaxies can reshape or even destroy these arms. Others argue that spiral arms can reform after disruption, much like rivers that carve new paths after floods. The truth may be a balance between both views. Astronomers model these possibilities with simulations, but reality is harder to capture. If the Milky Way ever lost its spiral arms, what would it look like? Perhaps a smooth oval, less distinct, less like a cosmic city. Or perhaps new arms would grow again, born from the rhythm of stars and gas. As we drift into rest, we can imagine these possibilities. The galaxy shifting slowly, changing its face across eons, yet still shining as a beacon of wonder in the night. At the very heart of every galaxy lies a region dense with stars, gas, and energy. This is the galactic core, a crowded space where millions of stars shine close together. Unlike the quiet suburbs of the spiral arms, the core feels alive, like the pulsing center of a living organism. In many galaxies, the core also contains a supermassive black hole, an object so heavy that even light cannot escape. Our own Milky Way is no exception. At its center rests Sagittarius A, a black hole weighing 4 million times more than the Sun. This invisible giant shapes the movements of stars around it, binding the core with gravity. Astronomers now believe that nearly all large galaxies have such black holes at their centers. These cores are the engines of galaxies, directing their rhythm, storing their history, and influencing their future. To picture the core is to picture a crowded city square, bright and full of motion, but surrounded by the calm sweep of spiral arms. It is the inner heart of the cosmic city, a place where energy gathers and radiates across the universe. The galactic core shines with a brilliance that seems both steady and strange. In some galaxies, the core is calm, while in others it blazes with overwhelming light. What fuels this radiance? And how can it remain stable for millions of years? One of the most striking examples is the galaxy M87. At its center lies a supermassive black hole that produces a jet of energy extending thousands of light years into space. In 2019, astronomers captured the first image of this black hole, revealing a glowing ring of gas surrounding a dark center. It was like looking directly into the beating heart of a galaxy. The core of the Milky Way is quieter, but still alive with motion. Stars orbit Sagittarius A in paths that reveal the black hole's pull. The brightness of these regions can be compared to a cosmic heartbeat, slow but steady, each pulse reminding us of the immense forces at work. When we imagine these cores, we can feel their rhythm, steady and deep, like the breathing of the cosmos itself. Scientists propose that supermassive black holes control the growth of galaxies through their influence on star formation. When they feed on gas, they release energy that can either trigger or suppress the birth of new stars. This creates a delicate balance, a cycle of nourishment and restraint. Yet questions remain. Could a galactic core grow quiet if its black hole stopped feeding? Would the stars lose their rhythm without that central force? Some believe the core could dim, changing the identity of the galaxy itself. Others argue that even if the black hole rests, the galaxy would continue to evolve under the pull of gravity alone. The debate is ongoing, and perhaps it will never be fully resolved. As we rest, we can picture the glowing cores scattered across the universe, each one a cosmic lantern, each one keeping time for its galaxy. They remind us that in the vast silence of space there is still a pulse, a sign of life written in light and gravity. Surrounding the core and stretching far outward is the galactic disk. This wide, thin structure holds most of the stars, planets, gas, and dust that make up a galaxy. It is like a giant plate spinning slowly in the darkness of space. The Milky Way's disk is immense. It stretches about 100,000 light-years across, but is only about 1,000 light-years thick. Within this flat structure lie the spiral arms, where new stars are often born from clouds of gas. Almost all of the visible matter in a galaxy belongs to the disk, glowing faintly but spreading endlessly. To imagine the disk is to imagine a painting brushed across the sky, thin but vast, filled with color and motion. It is the surface on which the galaxy draws its design, the flat stage where stars shine and planets dance. The disk is not empty, but alive with activity, and every star we see in the night sky belongs to this great cosmic plane. One of the quiet mysteries of the universe is why galactic disks are so flat. With so much matter, one might expect them to form spheres, yet instead they spread out into wide, thin layers. This shape seems natural, but its cause remains a question. When we look at galaxies like Andromeda, our nearest large neighbor, we see the same flat disk stretching across space. Observations through telescopes reveal its delicate structure, like a silver coin laid upon the blackness of the universe. The flatness is not fragile. It holds steady across billions of years, yet its origin is hidden in the distant past. Some disks show ripples or bends, signs that nearby galaxies may have disturbed them, but overall they remain remarkably even, as if drawn by a steady hand. To imagine such a disk is to imagine a cosmic painting stretched out for eternity, each brushstroke made of stars and light, filling the darkness with calm beauty. Astronomers suggest that the flat shape of a disk is the result of angular momentum. In the early universe, clouds of gas collapsed under gravity, but as they spun, their rotation pressed them into a thin sheet. Like a dancer spinning with arms extended, the galaxy stretched outward and flattened. Yet this explanation does not end the debate. Collisions between galaxies can warp or even twist disks into new shapes. Some scientists believe the Milky Way itself shows slight bends at its edges, perhaps caused by interactions with smaller companion galaxies. Others think the flatness is resilient. The disks always return to their balanced state after disturbances. If disks were not flat, the universe might look very different. Stars could move in chaotic orbits, and planets might never find stable paths. As we rest and drift towards sleep, we can imagine these immense disks lying across the cosmos, flat rivers of starlight, quiet foundations on which galaxies build their eternal cities. When galaxies drift through the universe, they sometimes cross paths. These encounters do not happen quickly. They unfold across billions of years. The result is not destruction, but transformation. Gravity draws the galaxies toward each other. Their shapes stretch and bend. New patterns appear. Our own Milky Way is moving toward the Andromeda Galaxy. In about 4 billion years, the two will meet and begin to merge. This will not be a violent clash as we might imagine, but a slow dance of stars and gas. During such collisions, clouds of gas are compressed, triggering waves of star formation. Astronomers call this a starburst, a sudden flowering of new suns across the galaxy. These events remind us that collisions create as much as they change, and the universe uses even chaos to paint beauty. When we imagine this future, we can see the sky reshaped, the Milky Way and Andromeda becoming one, their stars glowing together in a grand new pattern. One of the most gentle mysteries of galactic collisions is that stars almost never strike each other. Though galaxies seem dense, the space between stars is vast. When galaxies pass through each other, the stars slip past like dancers on a wide floor. Instead of crashing, they move gracefully, guided only by gravity. The antennae galaxies are a vivid example. They are in the midst of a collision. Their shapes stretched into long tidal tails that reach across thousands of light years. These tails resemble ribbons trailing behind the dancers, glowing arcs of stars and dust. The motion is slow, so slow that to us it appears frozen in time. Yet it is always unfolding. To watch these images is to feel the softness of cosmic movement, a waltz that spans millions of years. Collisions may sound violent, but in the language of the stars, they are closer to a tender embrace, a meeting that changes both partners forever. Astronomers believe that many collisions end in mergers, forming larger galaxies with new shapes. Spirals may blend into giant ellipticals, or two galaxies may join into an even grander spiral. Simulations show these outcomes, but the future of any one collision is uncertain. Questions remain about the fate of planets. Would the paths of worlds be disturbed? Would skies change dramatically for those who look upward? Some scientists suggest that most planets would survive unscathed, their suns carrying them safely through the encounter. Others believe some systems might be disrupted, their orbits altered by shifting gravity. If Earth still exists when the Milky Way meets Andromeda, the night sky will be breathtaking. Instead of one galaxy, two vast spirals will fill the heavens, slowly weaving into one. For now, it is only a vision, but it invites us to dream of skies transformed by the dance of galaxies. Galactic collisions leave marks behind, patterns carved into the fabric of the stars. These traces can appear as long tidal tails, as rings of stars, or as warped disks. They are like scars on the body of the universe, reminders of encounters that reshaped galaxies. The Cartwheel Galaxy is one of the most striking examples, observed by the Hubble telescope. It shows a bright ring of stars expanding outward from its center, the result of a past collision. Such rings are not permanent, but they can last for hundreds of millions of years. Tidal tails stretch like delicate threads, curling away from the main body of a galaxy. Warped disks show the tug of gravity bending what was once flat. These signs tell astronomers the story of past events, long after the main collision has ended. A single merger can take billions of years to complete, but its traces endure across cosmic time, like footprints left in sand that never washes away. It is mysterious how these traces can last so long in a universe where motion never stops. Why do tidal tails remain coherent instead of dissolving quickly into space? The Whirlpool Galaxy offers a clue. Its spiral arms appear twisted, distorted by the pull of a smaller companion galaxy. The disturbance has lasted for millions of years, shaping the galaxy's form in subtle ways. The arms carry the memory of the encounter, like folds in a vast cosmic painting. These folds do not vanish but hold their shape, stretched out across light years. To look at them is to see time itself captured in structure. The traces are not accidents. They are chapters of a story written in light. Each curve, each ripple, is a reminder that galaxies are not static but always interacting. As we imagine these traces, we might think of them as the wrinkles of age on the face of the universe, lines that tell us what has been lived. One idea is that the persistence of these traces comes from gravity itself. Stars and gas pulled into tidal tails remain bound to the galaxy's mass, held in long arcs that slowly evolve. This gravity acts like invisible glue, keeping the shape intact. Yet another possibility is that dark matter plays a role. If galaxies are surrounded by halos of unseen matter, then this hidden framework may preserve the structure of tidal tails and rings. Astronomers debate how much dark matter influences these outcomes, but without it, the shapes might dissolve more quickly. Without traces, we would lose the ability to read the history of galaxies, their collisions hidden in silence. With traces, we can follow the story, learning how galaxies grow and change. Each mark becomes a message from the past, a quiet whisper across billions of years. These whispers remind us that nothing in the universe is lost. Everything leaves a sign. Everything becomes part of the greater pattern. When galaxies finally merge, the result is a new creation. Two cosmic cities join into one, reshaping their streets, blending their stars. The process may take billions of years, but the end is unmistakable. Often the result is a larger elliptical galaxy, round and smooth, lacking the spiral arms that once defined its parents. Sometimes a new spiral can emerge, larger and grander than before. One famous example is Centaurus A. This galaxy bears the marks of a merger, with a striking disk of dust cutting across its bright core. The dust is the residue of a smaller galaxy consumed by a larger one. Today, Centaurus A shines as a reminder of this union. Astronomers believe that nearly every large galaxy has experienced at least one major merger in its lifetime. Mergers are not rare accidents. They are part of the natural life of galaxies, steps in their long journey across cosmic time. One mystery is how mergers influence the activity of supermassive black holes. When galaxies combine, their central black holes are drawn together. Do these unions trigger bursts of energy? Do they awaken sleeping giants? Observations suggest that this may be true. The galaxy NGC 6240 is a striking case. At its heart are not one but two supermassive black holes, remnants of a merger. They circle each other slowly, preparing one day to become a single, even larger black hole. Such encounters release enormous energy, enough to light the cores of galaxies for millions of years. The process is like two rivers joining, their waters mixing into a stronger current. For those who look on, the merger is a sign that nothing in the universe remains separate forever. Everything drifts together in time, and everything finds union in the end. Astronomers propose that galaxy mergers provide fuel for supermassive black holes. As gas and dust fall toward the center, the black hole consumes it, releasing powerful energy. This could explain the bright cores seen in many merged galaxies. Yet there are debates. Could a merger create a galaxy without a central black hole? Or is a black hole always inevitable? If mergers did not occur, would the universe contain fewer black holes? Fewer bright centers? The answers are still hidden in the dark. What is clear is that mergers shape the universe we see today. Without them, galaxies would be smaller, quieter, perhaps less varied. With them, the cosmos becomes dynamic, filled with structures of beauty and power. As we rest, we can imagine these unions unfolding, galaxies blending like colors on a canvas, creating new forms that glow for eternity. Hidden in the cosmic darkness is a form of matter we cannot see, touch, or detect with ordinary instruments, yet it silently shapes the motion of billions of stars. This is dark matter, a mysterious substance that does not emit, absorb, or reflect light. It reveals itself only through gravity, pulling on everything around it. In the 1970s, astronomer Vera Rubin made a discovery that changed astronomy forever. She found that stars at the edges of galaxies were moving far faster than expected. According to Newtonian mechanics, those stars should have been flung into space, drifting away from their galaxies. Yet, something unseen held them in place, as if a great invisible hand was keeping the galaxies bound together. That something was dark matter. Since then, Scientists have calculated that dark matter makes up nearly 27% of the universe's total mass and energy. Without it, the cosmic structures we take for granted, spiral galaxies, clusters, and even the great filaments of the universe could not exist. It is both absent and essential, an invisible framework upon which the luminous universe is built. What makes dark matter so haunting is its invisibility. Unlike gas or stars, it does not shine or glow, nor does it block the light behind it. Instead, its presence must be inferred indirectly, like footprints left in the sand. One of the clearest pieces of evidence comes from the Bullet Cluster, where two galaxy clusters collided violently. The hot gas, the visible matter, was displaced in one direction, but gravitational maps revealed that most of the mass lay elsewhere. This ghostly distribution matched what we now call dark matter. Even more striking is the way it bends light. Through a process known as gravitational lensing, background galaxies appear warped, stretched, and magnified, as if seen through a curved glass. Such effects cannot be explained by visible matter alone. And so, astronomers picture dark matter as a vast shadow enveloping galaxies, unseen yet always present. It is like a cosmic embrace, holding the universe together. And we are left to wonder, are we living inside a great, silent ocean of shadows, carried along by currents we cannot perceive? To explain this invisible glue, scientists have proposed bold ideas. One leading hypothesis is that dark matter is composed of exotic particles called WIMPs, weakly interacting massive particles. These particles would barely ever collide with normal matter, passing right through us and the Earth without notice. But their collective gravitational pull would be enough to bind galaxies. Other proposals suggest particles like axions or sterile neutrinos, each stranger than the last. Yet not everyone agrees that dark matter exists as a substance. Some physicists argue instead that our understanding of gravity itself is incomplete. Perhaps Newton's laws or even Einstein's theory of general relativity need to be extended. Modified gravity theories try to account for galactic motions without invoking dark matter at all. The debate remains open, because no experiment has yet detected a dark matter particle directly. It is a puzzle at the heart of cosmology, leaving us with profound questions. If dark matter is real, it may dominate the universe more than the stars themselves. But if it is not, then our most trusted theories about how the cosmos works may be flawed. Without dark matter, could galaxies truly hold together? Or would the universe dissolve into emptiness? Long ago, in the infant universe, matter was spread out like a thin mist. Ordinary gas alone could not have clumped together quickly enough to form galaxies. But dark matter, heavy and invisible, provided the scaffolding. Its gravitational pull gathered hydrogen and helium into denser clouds, sparking the first stars. Without this unseen framework, the universe would be a dim, diffuse place, never coalescing into the brilliant spirals and clusters we see today. Modern supercomputer simulations have confirmed this role. When cosmologists include dark matter in their models, galaxies appear naturally, clustering along vast filaments and nodes. Without it, the simulations fail, stars remain scattered, and cosmic structures never grow. Observations support this picture as well. Evidence shows dark matter influenced the universe more than 13 billion years ago, just after the first light emerged. Like an architect who never shows their face, dark matter quietly designed the cosmic cityscape, laying down invisible foundations so that stars could rise like towers of light. It is humbling to realize that the beauty of the night sky depends not on what we see, but on what we cannot. Despite this central role, dark matter remains elusive. How does it distribute itself within galaxies? Why do some galaxies appear to be dominated by it, while others contain less? Astronomers turn to dwarf galaxies, tiny, faint systems with very few stars, for answers. These galaxies often show evidence of enormous amounts of dark matter, far outweighing their visible matter. In this way, they act as laboratories, helping us glimpse the invisible scaffolding more clearly. It is as if dark matter is the skeleton of a galaxy, giving it shape and strength while remaining unseen. The visible stars are just the glowing skin stretched across this hidden frame. Yet, the skeleton does not always appear uniform. Some galaxies exhibit unexpected distributions, suggesting dark matter may behave in ways we do not yet understand. Such mysteries invite us to imagine galaxies not as solitary islands, but as luminous veils draped over a hidden web. The thought is both haunting and beautiful. Everything we admire in the night sky may be just the surface of something far deeper, shaped by a silent, invisible hand. One compelling hypothesis is that dark matter creates a cosmic web of vast, interconnected networks stretching across billions of light years. In this vision, dark matter filaments link galaxies together, forming a framework upon which cosmic structures are built. The luminous galaxies we see are merely pearls strung along these unseen threads. Yet questions remain. Does dark matter remain constant across time? Or does it evolve? Some suggest it might decay slowly, changing the balance of forces in the universe. Others argue that it could interact with itself in subtle ways, altering the shapes of galaxies. The debate reflects the profound uncertainty surrounding this subject. What would happen if dark matter were to vanish? Galaxies might unravel, stars drifting away into the void, leaving behind a universe far darker and lonelier. Contemplating this possibility makes the present cosmos seem fragile, almost temporary. The galaxies we admire could be fleeting patterns, held together only as long as this invisible glue persists. It reminds us that permanence is an illusion, and even the stars depend on hidden forces to endure. Dark matter does more than shape individual galaxies. It influences the very architecture of the cosmos. From galaxy groups to massive clusters, it provides the gravitational glue binding them together. Observations of the Virgo cluster reveal this clearly. Though thousands of galaxies shine brightly within it, their combined mass is only a fraction of what holds them there. The rest must be dark matter, outweighing visible matter many times over. Without it, such clusters would simply fly apart, the galaxies drifting away like dust on the wind. Instead, they remain tethered, forming immense cosmic cities bound by invisible gravity. On even larger scales, dark matter weaves the universe into filaments and voids, arranging galaxies into patterns that echo across billions of light years. The cosmic web we see today is not random. It is the fingerprint of dark matter, guiding the growth of structure since the dawn of time. To imagine the universe without it is to imagine a sky stripped of order, where stars and galaxies scatter endlessly with no shape, no pattern, no frame. Dark matter, unseen and silent, is the artist that gives the cosmos form. The greatest mystery is whether dark matter also influences the expansion of the universe itself. We know that dark energy pushes galaxies apart, accelerating cosmic growth. But does dark matter play the counterbalance? Tugging back, slowing the expansion. Some evidence suggests it might. The galaxy cluster Able 1689 offers a vivid demonstration. Its immense mass, most of it dark matter, bends light from background galaxies into dramatic arcs. This gravitational lens shows just how powerful the invisible component must be. It acts like a vast, invisible net, keeping the universe's fabric from unraveling too quickly. But the details remain uncertain. Does dark matter resist dark energy? Or does it simply coexist, each shaping the universe in its own way? Astronomers continue to measure, simulate, and debate, yet the truth hides behind a curtain of shadows. To think of dark matter as invisible strings stretched across the cosmos is to imagine the universe as a great instrument. As long as those strings remain, the symphony continues. But if they were ever to break, what music would remain? Some cosmologists believe that dark matter provides a stabilizing counterweight to dark energy, slowing the universe's expansion and preventing it from tearing itself apart too quickly. In this view, it is not just glue but balance and unseen harmony between opposing forces. Yet others speculate that dark matter may not last forever. What if it decays slowly over cosmic time, its presence fading into the void? If so, the universe of the far future could be very different from the one we know. Galaxies might lose their bonds, drifting into isolation. Clusters could dissolve, leaving only lonely galaxies in an ever-darkening sky. The night we see now, rich with constellations and glowing spirals, could someday vanish into emptiness. Such possibilities stretch our imagination and deepen our sense of wonder. For now, dark matter endures, shaping every pattern of stars above us. But the question lingers: what would become of the universe if this invisible glue were gone? In the quiet embrace of dark matter, where galaxies are held together like stars in a gentle web, the universe whispers of unseen bonds. Subscribe to Cosmic Sleep Science and continue exploring these invisible wonders with us. Close your eyes and imagine a star so large that its blue light shines across space. A giant blazing at more than 20,000 degrees Celsius, glowing hundreds of thousands of times brighter than our sun. Its heart alive with the dance of fusion. Hydrogen becoming helium, helium turning into carbon, oxygen, and finally into iron. Every stage of burning marking another chapter in its long life. But like all stories, this one has an ending. Because fuel is not infinite. And when the last reserves of energy fade away, the balance between pressure and gravity breaks. The core begins to collapse. And what was once a brilliant beacon slowly approaches its final moment. Science tells us that stars more than 8 times the mass of our sun cannot simply fade into quiet embers. Instead, they explode, releasing everything in one last magnificent outburst. The event we call a supernova, a cosmic farewell that lights up the universe with a beauty mixed with tragedy. It is natural to wonder, what happens to a star when it no longer has the power to shine? What remains when the fire has burned through every last atom of fuel? The answer lies in the heart of collapse itself, in the path that leads toward the dark mystery we call a black hole. And as you listen, let yourself drift into the slow rhythm of creation and destruction. Light giving way to darkness, energy surrendering to silence, a reminder that even the brightest fire must one day rest, leaving behind something stranger, deeper, and far more powerful than we can see with our eyes. When the final spark fades, the star explodes in a supernova, brighter than 100 billion suns, so powerful that it can be seen across galaxies, even from the surface of Earth. In those moments, the star seems to defy death by shining in a brilliance beyond imagination. Yet this is only the beginning of something more profound. For within the heart of that explosion, the core continues its collapse, shrinking smaller and smaller, density rising past the limits of ordinary matter, until atoms themselves are crushed and space bends under the pressure. What forms as a black hole, a silent shadow born from overwhelming force. Scientists recall the event of 1987, when a supernova lit up the night sky, known as SN 1987-8, the clearest example we have observed with human eyes and instruments. Through it, we came to understand how endings and beginnings in the cosmos often exist as one. Imagine a glowing wave of light rushing outwards, and then, as it fades, silence. A quiet so deep that it feels like the universe itself has paused to take a breath. Black holes are not created in peace but in violence, yet their presence afterward is one of stillness, an invisible anchor hidden in the fabric of space. As you think of this picture, allow yourself to float with the thought of energy released and then gone, brightness followed by calm, and recognize how the universe moves in rhythms of expansion and rest, not unlike the rhythm of your own breathing tonight. Not every giant star meets the same fate, for the outcome depends on size. Stars more than 20 to 25 times the mass of our sun collapse into black holes, while stars between 8 and 20 times the mass of our sun may collapse into neutron stars instead. Both are dense beyond imagination, but the difference is striking. A neutron star is no larger than a city, yet holds more mass than the sun, while a black hole hides itself completely, becoming a well in space from which nothing can escape. even light. Scientists describe that if you could take just a spoonful of matter from a black hole, it would weigh billions of tons. Such is the power of compression that defies every sense of scale we know. We may wonder how this compares to our own star, the sun that gives us warmth and life each day. If the sun somehow collapsed into a black hole, it would not swallow Earth instantly. Our planet would keep orbiting around the invisible center as if nothing had changed. The difference would be in light, for darkness would reign in place of day. This thought draws us deeper into reflection. What seems eternal in our daily life is not immune to the laws of cosmic change. Everything is bound by the flow of time and energy. Yet in this flow there is a strange comfort, knowing that we are part of the same cycle as stars. Bright for a while, then quiet, carried along by forces much greater than ourselves. And so we listen, and we drift, guided by the story of stars collapsing into silence. Among the many types of black holes, the most common are stellar black holes, born from the collapse of massive stars. These objects usually hold a few times, or perhaps a few dozen times, the mass of our sun. Hidden from direct sight, but revealed through the way they pull on nearby stars and gas. When matter falls toward them, it heats up and glows in X-rays, creating a signal that astronomers can trace across the sky. In the Milky Way alone, there may be tens of millions of stellar black holes, quietly moving with the stars, invisible yet present. Their small size in cosmic terms makes them difficult to find, yet their numbers remind us that black holes are not rare or distant curiosities, but familiar neighbors in the galactic sea. Imagine drifting in space and knowing that countless of these dark wells surround you, scattered like hidden stones beneath the surface of an endless ocean. The thought may bring a quiet shiver, yet it also carries wonder. For the universe holds far more than what our eyes can see. As you listen tonight, let this image soften into calm. Many black holes scattered across the galaxy, each one a silent witness to the life and death of stars. Far grander in scale are the supermassive black holes, objects so immense that they weigh millions or even billions of times more than the sun. These titans rest at the centers of galaxies, shaping the stars that form and guiding the structure of their spiral arms. At the heart of our own Milky Way lies Sagittarius, a star, a black hole with the mass of about 4 million suns. Though we cannot see it directly, we know it is there from the way stars orbit with incredible speed around an invisible point. It is natural to wonder if every galaxy shelters such a giant in its core. And many astronomers believe the answer is yes. These black holes may have played a central role in the birth of galaxies themselves. The presence of something so heavy yet unseen reminds us that cosmic order is often held together by forces beyond our senses. Picture the calm center of a storm where everything is drawn inward and held still. That is what a supermassive black hole is for a galaxy, both dangerous and stabilizing, both hidden and essential. As you let this thought sink in, imagine yourself at the quiet center of your own life, watching the motion around you, steady and at rest. Between the stellar black holes and the giants at galactic centers lies a class that is harder to find: the intermediate black holes. These objects are thought to be formed when several smaller black holes merge together, or when a massive star cluster collapses into a single core. Their size places them in the middle, larger than any single star could produce, yet far smaller than the monsters at galactic hearts. Astronomers long searched for signs of them, and in the year 2020, a discovery offered proof. The instruments known as LIGO detected the waves of two black holes merging to create one with a mass about 142 times that of the Sun. This was the first clear evidence of an intermediate black hole, still so rare and mysterious that we may have seen only the beginning of their story. Reflecting on this discovery, we feel as if we have just touched the tip of a vast iceberg, most of it still hidden below the surface, the unknown stretching outward in silence. These black holes remind us how much remains unseen in the universe, and how even in the age of science we stand at the edge of wonder, knowing that mysteries wait patiently for us to find them. like gentle shadows drifting far away, quiet yet immense. In the year 1916, while the world was shaken by the battles of the First World War, a German physicist named Karl Schwarzschild was serving at the front. Surrounded by the noise of shells and the weight of conflict, he turned his attention to the new equations published by Albert Einstein. From within the trenches, he solved them in a way no one had before. What he found was a description of space bending so strongly that not even light could escape. He called it the Schwarzschild radius, a mathematical boundary that marks the edge of a black hole. Though he himself did not live long to see how powerful this idea would become, his work stood as the first exact formula of what we now call a black hole. In the midst of destruction and war, he had drawn the invisible frontier of the cosmos, a place where time and space fold into silence. Thinking of this moment gives a strange sense of wonder. Between fire and smoke, a single human mind reached across the universe and touched an idea that would outlive centuries. Between chaos and fear, he outlined the border of an abyss, as if to remind us that even in darkness, discovery can be born. And so the story of black holes begins not with telescopes or machines, but with a man writing on paper under the weight of history, showing us that thought itself can light a path into the most hidden corners of the cosmos. Einstein had opened the door with his theory of general relativity, a vision of space and time woven together. But even he was cautious about the extreme predictions that came from his own work. He called black holes strange solutions, mathematical curiosities that seem too unreal to exist in nature. His hesitation reminds us that even great minds hesitate before mysteries. For to imagine a place where light is trapped and time bends infinitely was almost too much for science in the early 20th century. Still, the equations remained, quietly insisting on their truth, waiting for decades until technology and observation could catch up. Only in the middle of the 20th century did astronomers begin to accept that black holes might not just be symbols in a theory, but real objects in the sky. This long delay shows us how human understanding often takes time to grow, and it leads us to reflect. If even Einstein himself doubted black holes, how certain can we be of anything? Perhaps the lesson is that mystery and uncertainty are not failures, but companions on the journey of discovery. As you listen now, let the thought of patience and slow unfolding rest in you. Knowledge blooms not all at once, but step by step, as if the universe wants us to learn in rhythm with its own vast breath. The turning point came with the stars. In the year 1964, astronomers studying X-ray signals discovered a source in the constellation of Cygnus. They called it Cygnus X1, and soon realized that the strange light could only be explained if a black hole was pulling matter from a nearby star. For the first time, humanity had indirect evidence that black holes were not only possible, but real. The discovery was made through international cooperation, with teams sharing data across borders, proving that the mysteries of the sky call us to work together. Among those who followed this research was Stephen Hawking, who once made a famous bet with a colleague that Cygnus X1 was not a black hole. Yet as the evidence grew stronger and stronger, he conceded, admitting that the hidden well of gravity was indeed there. This story captures the heart of science. Bold skepticism giving way to humble acceptance when facts are undeniable. From an idea once dismissed as fantasy, we had found a real shadow in the heavens. And in that moment, black holes crossed from imagination into reality. As you rest tonight, let yourself linger on this truth, that through doubt and persistence, humanity can trace even the darkest outlines of the universe. And you may ask yourself, what turns strange ideas into scientific certainty? Perhaps the answer lies in patience, evidence, and the willingness to see beyond what feels possible. At the edge of every black hole lies a boundary so strange that even light cannot cross it. This boundary is called the event horizon. It marks the invisible surface beyond which nothing can return. The event horizon is not a solid wall, but a threshold, a point where escape velocity equals the speed of light. And because nothing can travel faster than light, this frontier is absolute. Scientists describe its size through the Schwarzschild radius, a value that depends only on the mass of the black hole. A small black hole a few times heavier than the Sun may have an event horizon only a few kilometers wide, while a giant black hole at the center of a galaxy can have one that stretches across billions of kilometers. Though invisible, the horizon acts like the ultimate border of space itself. Imagine it as a silent line drawn in the fabric of the universe, a place where motion flows in only one direction, inward, never outward. It feels like a cosmic shoreline, but one where no wave can return. It is natural to ask what would happen if an astronaut touched this horizon. Would time stop? Would they vanish? Or would they simply cross into a place we cannot see? The mystery lingers, as vast and quiet as the night sky. From far away, the event horizon appears like a stage for illusions. Light bends as it struggles to escape. Signals stretch and fade. And to an outside observer, an object falling toward the horizon seems to slow down, appearing to freeze just at the edge. In truth, the object continues on, but its light grows weaker and redder until it disappears. Radio signals, too, will fade, thinning like a whisper carried away by endless distance. This strange effect comes from gravity pulling on time itself, slowing the clock of the falling traveler. So while the astronaut feels their descent as natural and unstoppable, those watching from safety would see them locked forever at the border, caught in a picture that never changes. From this distance, the scene feels eerie, as though the universe has created an eternal mirage, something trapped at the rim of darkness yet never crossing. We might say it looks like the cosmos is holding its breath, watching an image linger that should have already passed. The event horizon is more than a frontier. It is a place where perception itself begins to break, where time divides into two versions, one outside and one within, both real yet never touching. For decades, the event horizon remained a concept in equations, unseen and unproven. Then in 2019, astronomers unveiled the first direct image of a black hole, the famous picture of the giant called M87 star, more than 50 million light-years away. In that image, we do not see the black hole itself. We see its shadow, the dark circle where the event horizon blocks light, surrounded by a glowing ring of matter heated to millions of degrees, gas and dust spiraling faster than any storm on Earth, creating light so fierce that it shines across galaxies. That bright halo outlines the invisible border, making it visible for the first time. To the eye, it resembles a cosmic eclipse, a permanent dark sun surrounded by a fiery crown, a solar eclipse frozen for eternity. This picture changed our understanding, turning theory into vision, turning imagination into proof, yet it raises its own question. Are we seeing the black hole itself, or only the shadow it leaves on the universe? Perhaps what we witness is not the object, but its absence, the silent mark of a place where light itself is taken, and in that silence lies both beauty and fear. At the very center of a black hole lies the singularity, a point where density becomes infinite, and our familiar laws of physics collapse. In this place, space and time themselves end. Gravity is so extreme that all paths lead inward, matter compressed beyond comprehension. It is the ultimate limit of what we can understand. Some scientists describe it as the hidden heart of the black hole, a place where known physics fails, a mysterious core wrapped in shadow. No light can escape, no signal return, and we can only model what happens with equations and imagination. The singularity may represent more than destruction. It may be a clue to new physics, a boundary between what we know and what we have yet to discover. Perhaps it is not a point but a window into a deeper theory, a structure waiting to be unveiled. And we can ask, could the singularity be simply a sign that our understanding of nature is incomplete? A placeholder for knowledge we have not yet grasped. As you drift through this thought picture, the center of the black hole, not as a threat, but as a silent teacher, challenging our certainty and inviting us to wonder, reminding us that even the strongest laws have limits, and that curiosity can travel to the darkest corners of the universe, beyond light and time. Some theories propose that the singularity might not be a true point of infinite density, but instead replaced by a quantum structure. In models that combine gravity with quantum mechanics, the classical singularity is smoothed out, replaced with a complex geometry at the smallest scales. String theory and quantum gravity suggest that space itself may be woven differently near the core. But so far, no direct observation confirms these ideas. Simulations on computers offer glimpses, yet the truth remains hidden. The deeper we look, the more fragile our certainty seems. Each layer of knowledge reminds us of the vast unknown. And the closer we get to the heart of a black hole, the more we feel the fragility of human understanding, like sand slipping through fingers. Yet we continue to explore, to calculate, to imagine. For the singularity is both a challenge and a call to push the limits of what science can reach. As you listen tonight, consider how the universe allows us to approach its extremes without ever fully grasping them, and let the thought of hidden knowledge settle gently, like quiet shadows at the edge of sight. Physicists have long sought to model the collapse of a star into a singularity using supercomputers. These simulations recreate the extreme pressures and densities at the core of dying stars, helping us estimate how matter behaves when crushed beyond the scale of atoms. Imagining the interior of a black hole is like trying to picture what lies inside a sealed box that cannot be opened. Yet even without direct access, we can explore its effects on the universe, predict the behavior of light and matter near it, and understand the flow of energy and gravity that surrounds it. These models are a testament to human ingenuity, a bridge from theory to insight, and they also raise questions. Could the singularity be the key to unlocking new physics? A hidden doorway beyond Einstein and quantum theory. The black hole challenges us to rethink space, time, and reality itself. And as you imagine this silent core, dense and unknowable, let it drift into your thoughts. A reminder that the universe is vast, full of secrets, and patient, waiting for curiosity and imagination to meet it. Around many black holes lies an accretion disk, matter spiraling inward in a cosmic whirlpool, heated to millions of degrees as friction and gravity squeeze it into light. The disk glows in X-rays and gamma rays, making the black hole visible indirectly. Without it, the dark center would remain completely hidden. The disk is a swirl of energy and danger, a spinning halo of fire surrounding an invisible abyss. Its motion hypnotic and fierce. Matter races around the black hole at enormous speeds, each particle following the curve of space-time. The accretion disk is not just a source of light, but also a tool, allowing astronomers to detect and measure black holes across the universe. Imagine a giant vortex of fire wrapping around a shadow, a deadly dance where energy is released with every orbit. It is natural to ask what keeps this infernal circle shining so brightly, why the light does not fade even as matter is pulled inward. The answer lies in physics, in the conversion of gravitational potential energy into radiation, a process far more efficient than nuclear fusion. A cosmic furnace fueled by the very pull of gravity. The energy released by accretion disks is staggering, more efficient than the fusion reactions powering stars. Up to 40% of a particle's mass can be converted into pure energy. A single gram of matter spiraling inward produces more energy than an entire nuclear bomb. This shows that black holes are not merely sinks, but engines, turning destruction into radiant light. The power they release illuminates galaxies, drives jets, and heats the interstellar medium. They are both devourers and creators, a paradox of the cosmos. The disks act as cosmic lighthouses, and their brilliance is a reminder of the scale of forces in the universe. The energy radiating from these disks dwarfs any human experience. Yet in this overwhelming power, there is beauty and symmetry. The laws of physics elegantly converting matter into light. And as you picture this flow of energy, imagine the disk spinning silently, its light a constant in the darkness, a pulse that guides our understanding of the invisible heart it surrounds. A cosmic fire we can witness from billions of light years away. Jets often emerge from the poles of black holes, Streams of charged particles launched at nearly the speed of light, extending thousands of light years into space. Visible in radio waves and other wavelengths, these jets are powered by the same energy that fuels the accretion disk, yet focused into narrow, almost unnatural beams, like cosmic lighthouses shining across intergalactic darkness. They carry away angular momentum, allowing more matter to fall inward, and in doing so they shape galaxies and cosmic structure. Their scale is almost unimaginable, stretching across distances larger than entire star systems. Yet their origin lies in the invisible, spinning core, a reminder that even unseen objects can influence the universe profoundly. It is natural to wonder why black holes can both swallow matter and simultaneously launch it across space. The process is still a frontier of astrophysics, a place where observation meets theory and where every discovery opens new questions. As you picture these jets, imagine light and matter arcing outward like a cosmic signal, a bridge from darkness to the observable universe. A reminder that black holes are not mere voids, but active participants in the story of space. The gravity of a black hole is unlike anything we experience. Near the event horizon, the force is so strong that the escape velocity equals the speed of light. Nothing can resist. Even light is trapped. The pull is concentrated into a region so small that it is hard to imagine. A black hole 10 times the mass of the Sun may have a radius of only a few dozen kilometers, compressing the Sun itself into the size of a city. It is a pit without bottom, a well that swallows everything, from matter to imagination. Tossing even a grain of sand into such a void would send it on a one-way journey into darkness. The force bends space itself, warping paths and slowing clocks. It is a place where Newtonian intuition fails, a place where the mind must stretch to grasp reality. Thinking of this pull can evoke awe and unease. The immense gravity is not just a physical effect, but a philosophical reminder. The universe can compress both matter and certainty into a single point. And in this compression, we glimpse the limits of our understanding. What happens when we cross that threshold is a question for both physics and imagination. And as you reflect on this gravity, allow yourself to drift, feeling the pull without fear, carried by thought into the silent depths. Objects falling into a black hole experience spaghettification, stretched into long, thin strands by tidal forces. The difference in gravity between the head and feet of a falling object becomes enormous, pulling it into a shape resembling an endlessly stretched noodle. The effect is extreme near small black holes, but less noticeable near supermassive ones. Yet the principle is the same. Matter is elongated by differences in gravitational pull. Every particle follows space-time, drawn along curves dictated by the mass at the center. The image of spaghettification captures both danger and strangeness. It is a visual metaphor for the limits of physical law. We may ask if all matter, regardless of composition, must undergo the same fate when approaching the event horizon. And the answer seems yes, for gravity is impartial, and its pull universal. Imagining this slow stretching can feel hypnotic, a reminder of the strange, elegant, and sometimes terrifying logic of the universe. A place where size, distance, and scale behave in ways our senses cannot fully grasp. Comparing a black hole to Earth or the Sun makes its extremes clearer. A black hole with 10 times the Sun's mass, but only a few dozen kilometers wide, concentrates mass into an unimaginable density. The Sun compressed into a city is almost incomprehensible. And yet gravity is not only local but absolute, warping space and time around it, pulling on matter and light, bending trajectories, and capturing imagination itself. It is a reminder that black holes do not merely affect matter, but also our understanding. Their presence challenges our assumptions. Their scale dwarfs familiar objects, and they make us reflect on the smallness of human perception. The force of gravity is the sculptor of light and time. And as you picture this extreme compression, let it drift into your mind. A silent, powerful lesson in the limits of scale and the persistence of natural law. A reminder that in the universe, Gravity can not only move mountains but also erase worlds from sight. Near a black hole, time itself stretches and slows, a consequence of Einstein's theory of relativity. Clocks close to the event horizon tick more slowly than those far away, a phenomenon called time dilation. 1 hour for an observer near the black hole could equal years for someone at a safe distance. The effect is not science fiction, but a real physical outcome of extreme gravity. In thought, we can imagine standing at the rim of a black hole and watching the universe age in fast motion while our own moments stretch into eternity. This bending of time invites questions. Could time travel ever exist if we simply approach such a gravitational well? The universe offers the closest analog to time machines through the warping of space-time. And yet, the effect is subtle in smaller black holes and extreme near the supermassive giants at galactic centers. It is a poetic and literal reminder that time is not absolute, but relative to space and mass, letting us reflect on the impermanence of moments and the elasticity of experience itself. The mind drifts along with this stretching, imagining 1 instant becoming 1,000 outside, and 1 second feeling infinite within. Movies like Interstellar illustrate time dilation, showing a crew spending hours near a black hole while decades pass on distant planets. The depiction is scientifically guided by Nobel laureate Kip Thorne, ensuring realism in the bending of time. These fictional images allow us to glimpse what extreme gravity does to reality, and to think about time as a flexible medium, not a rigid constant. 2 worlds moving side by side, yet experiencing duration differently. 1 minute here may equal a lifetime there. The parallelism is both fascinating and humbling. It reminds us that our usual experience of time is local, and in the cosmos, time flows differently depending on where we stand. Considering this in the calm of night lets the mind expand, imagining simultaneous experiences stretching across space, a quiet meditation on relativity, on perspective, and on the intimate connection between gravity and the passage of moments. Even in everyday life, time dilation matters. For GPS satellites orbiting Earth, clocks tick slightly faster than those on the surface. Engineers must correct for this tiny difference. A few milliseconds per day would accumulate errors in navigation if unaccounted for. The principle proves that time is intertwined with space and gravity, not just a theoretical curiosity. Though small, the effect is measurable, a testament that Einstein's insights into the relativity of time hold true everywhere, not only in thought experiments, near black holes or in laboratories, but also in our technology. These differences, though minute compared to extreme black holes, remind us that time is never absolute, and that even the ordinary is shaped by the universe's geometry. We might wonder, if time bends and stretches with mass and gravity, is any moment universal? Or is every instant a reflection of the place where it occurs? And as you reflect, let yourself relax into the rhythm of relative time, imagining the universe as a gentle, malleable river carrying experience along its curved paths. From the outside, it appears that matter vanishes when crossing the event horizon, swallowed by darkness without return. Yet within the black hole, the matter still exists, compressed into the singularity, hidden from view, like a drop falling into an ocean. It merges and disappears to the eye, but remains part of the whole. The disappearance is only apparent, a visual illusion caused by extreme gravity. Light cannot escape to inform observers of the true fate of the matter. And yet it is there, part of the black hole's mass and structure. This duality is one of the strangest properties of black holes. Matter gone yet not gone, invisible yet existing. The metaphor of water slipping into the sea captures the essence. The black hole is container of secrets, of energy and mass folded beyond perception. We might ask if information, the details of the object itself, can also vanish. And physics wrestles with this question, trying to reconcile disappearance with the unbreakable laws of nature. The so-called information paradox asks if data swallowed by black holes is lost forever. Stephen Hawking initially argued that information could vanish completely, challenging fundamental principles of physics. Later, he revised his view, proposing that subtle quantum effects could allow information to escape. The paradox remains one of the deepest questions in modern science, a test of how gravity, quantum mechanics, and the nature of reality coexist. The mystery transforms black holes into a proving ground for human intellect, where theoretical exploration meets the limits of observation. Pondering this invites awe, for in contemplating disappearance and persistence, we confront both the universe and the boundaries of knowledge. Black holes test not only matter and light, but also imagination and reason. And as you consider these questions tonight, allow the paradox to drift softly. A silent challenge at the edge of thought. A reminder that some mysteries are both unreachable and beautiful. Hawking radiation reveals another strange property. Black holes can slowly evaporate, matter and energy returning as faint radiation over immense timescales. Small black holes could vanish within a time far shorter than the age of the universe, while massive ones persist longer. This radiation is like the final embers of a dying fire, a subtle glow emerging from the darkness, offering a path for matter and energy to escape after all. The image of a black hole gradually shrinking and disappearing evokes both melancholy and wonder, for what seemed eternal is finite. What was hidden becomes faintly visible. We can imagine the universe witnessing the final whisper of a black hole, fading into quiet. And naturally we ask, could all black holes one day vanish completely, leaving nothing but traces? The ultimate silence of the cosmos. And as you drift toward sleep tonight, let the thought of this slow vanishing rest in your mind. A gentle meditation on impermanence, the cycles of energy, and the quiet rhythm of the universe itself. If you've enjoyed drifting through the mysteries of black holes tonight, please like and subscribe to Cosmic Sleep Science to join us on more gentle journeys through the universe's wonders. In 1990, the spacecraft Voyager 1 looked back one last time before leaving the solar system. From a distance of more than 6 billion kilometers, it captured a single image of Earth. The dot was so small that it filled only a fraction of a pixel. Carl Sagan later called it the pale blue dot, a phrase that would echo across generations. He reminded us that everything we have ever known, every story, every love, every war, every invention, all happened on that fragile speck of light. In the cosmic scale, it is less than a grain of dust suspended in a vast sunbeam. The photo did not just show a planet. It showed perspective. The Earth, shimmering softly in the blackness, revealed both beauty and vulnerability. Its thin atmosphere, its delicate balance, its uniqueness as the only known home of life, all contained in that tiny dot. Voyager did not just send data, it sent us a mirror. And in that mirror, we saw how small we are and how rare the conditions of our world might be. The pale blue dot became not only an image, but also a lesson, a reminder of humility and of the fragile wonder of life. The pale blue dot also carries a mystery. If Earth is so small in the immensity of the universe, is it truly special? Or is it simply one of many lights scattered in the cosmic sea? The photograph gives no borders, no nations, no divisions. Just a single point of light, fragile and faint, glowing against a dark infinity. It looks like a droplet suspended in a boundless ocean, delicate and yet luminous. A reminder of how tiny our world is compared to the galaxies beyond. The image is silent, yet it whispers of unity. It tells us that from this distance, all human differences vanish. All our triumphs and tragedies collapse into a dot barely visible. When seen through Voyager's eye, the Earth is not a stage for power. It is a glimmer, a fleeting sparkle, a small island of color in an endless black sea. And yet within it the oceans move, forests breathe, and humans dream. The mystery remains whether this is the only island or whether countless others shimmer unseen across the deep universe. Some scientists argue that Earth may be truly unique, a planet where complex life emerged under rare and fragile conditions. Perhaps the mixture of water, atmosphere, and stable climate is a coincidence so unlikely that it has happened only once. On this dot, in this corner of the galaxy, others suggest the opposite, that the cosmos is too vast for life to be confined here, that hidden among billions of stars are countless planets with oceans, clouds, and perhaps voices waiting to be heard. The pale blue dot, then, is not just a photograph. It is a question. It asks whether we are alone. The debate continues. Some say Earth is extraordinary. Others say it is ordinary. Yet both views highlight the same truth, that we do not know. The silence of the universe holds the answer. If Earth is unique, then we must guard it carefully, for it is the only home we will ever have. If it is not unique, then somewhere in the distance we have cosmic neighbors, perhaps watching their own pale dot, perhaps wondering about us. Either way, the pale blue dot reminds us of our place, small yet filled with meaning, fragile yet luminous in the darkness. The search for other worlds began as a dream. For centuries, humans looked at the stars and wondered if other Earths might circle distant suns. The dream became science when telescopes like Kepler were launched into space. Its mission was simple yet profound: to look for the tiny dimming of starlight that signals a planet passing in front of its star. In 2009, Kepler began its watch, and soon it revealed a galaxy of worlds. More than 2,600 planets confirmed during its mission, and thousands more candidates. Some of these worlds were rocky, some were gas giants, and a few lay in what scientists call the habitable zone, a region where temperatures might allow liquid water. Today, more than 5,000 exoplanets have been discovered, each one a reminder that our solar system is not alone. Each discovery expands the map of the possible. The numbers suggest that planets may be more common than stars themselves. It means the universe could be filled with distant islands of stone and air, waiting silently, circling their suns in endless night. The search is far from over, and each discovery pulls us closer to an answer to the old question: are we alone? The mystery deepens when we look at systems like TRAPPIST-1, a small cool star just 40 light-years away. Around it circle 7 planets, all close in size to Earth. 3 of them lie in the habitable zone, a region where oceans might form. It is like finding 7 islands clustered together in the ocean of space. From our distance, they are only points of light. Yet we imagine their skies, their mountains, their seas, perhaps quiet and lifeless, perhaps filled with unseen motion, perhaps waiting for discovery. Each exoplanet is a clue, a message written in light, telling us that the conditions for life may not be rare. The silence of their signals keeps us wondering, are they deserts or gardens? The planets of TRAPPIST-1 remind us of archipelagos across Earth's oceans, separated yet connected, hidden yet visible from above. The universe is vast enough to hold countless such islands. The mystery is whether any of them glow with life. The image is slow, gentle, a reminder that in the dark sea of stars, there may be shores unknown, worlds that watch their own pale dots in their night skies, perhaps wondering about us as we wonder about them. Some scientists believe that microbial life may be common. Perhaps it thrives beneath icy crusts or within oceans of exoplanets. Simple cells may be the natural outcome of chemistry repeated across billions of worlds. If so, then the universe could be alive in countless hidden ways. Others are more cautious. They argue that complex life, the kind that builds tools and stories, may be rare, perhaps vanishingly so. Earth may be an exception, not the rule. The silence of the cosmos may be telling us this. The debate continues. Some call it the Great Filter, the idea that many steps must succeed for intelligence to rise, and most worlds may fail somewhere along the chain, perhaps at the start, perhaps much later. If microbes are common but civilizations are rare, then we may still be alone in thought. Even if not in biology, yet hope remains. Because if one day we detect a signal, a whisper from a distant sun, we will face a question not of science alone but of humanity. What will we say? How will we greet them? What story will we tell of this pale dot, where humans looked up and dared to wonder? In 1977, the Voyager spacecraft carried more than instruments. It carried a gift, a golden record placed gently on its side. designed as a message from Earth to the cosmos, a time capsule and a greeting, an introduction of who we are. The golden record contained 115 images, from landscapes to human faces, from mathematics to DNA. It carried sounds of wind and thunder, the calls of birds, the laughter of a child, and greetings in 55 languages spoken across Earth. Music filled its grooves, from Bach to Beethoven, from traditional songs to a Navajo chant, all chosen to represent the breadth of human culture. The record was not a claim of power, but a gesture of openness, a message cast into the sea of stars with the hope that someone someday might find it. Voyager 1 now travels more than 24 billion kilometers from Earth, beyond the edge of the solar system, carrying that golden circle still, drifting silently in interstellar space. It is both a machine and a messenger, and its record spins as an offering, a reminder that humanity, small as a dot, still chose to speak to the universe with music and light. The mystery lies in whether this message will ever be found. The golden record is like a letter adrift in an ocean so vast that its shores may never be reached. Yet the possibility lingers, and with it a quiet hope. Radio signals from Earth have already created a sphere around us, a bubble 200 light-years wide, filled with television broadcasts, radar pulses, and whispered signals of our presence. Faint but spreading, perhaps somewhere in that bubble a civilization could already be listening. Perhaps they hear fragments of our voices, our songs, our pulses of thought, carried by light across the void. The golden record is different, more intentional, like a crafted poem compared to scattered words. It is a signal of who we are, not just noise. We imagine it drifting, slow and silent, past stars and clouds of dust, like a bottle cast into a cosmic sea, carrying within it the essence of Earth. Whether it is ever found or not, the record is already a symbol. It tells us that we chose to send ourselves outward, to say we are here, and that in itself carries meaning, even if no one listens. Some imagine that if another civilization finds our message, they might understand. Perhaps they will decode the diagrams, listen to the music, and recognize that they are not alone. Perhaps they will smile at the laughter of a child recorded on a fragile disc from a fragile world. Others argue that the signal may never be heard. The noise of the cosmos may swallow it. The record may drift forever unnoticed, a silent relic in endless night. There is also debate over whether sending messages is wise. Some fear that to announce ourselves is to invite danger, that in the vast unknown we should remain silent. Yet others see it differently. They say that to send a message is to fulfill our nature, to reach out, to connect, to declare that life here learned to dream. If the record is never heard, it still matters, for it changes us. It shows that humanity once chose to represent itself not with weapons but with music, not with conquest but with curiosity. And if it is heard, then it will carry the story of Earth across the stars, a pale dot that dared to speak, and to wonder who might listen in return. Spacecraft are more than machines. They are messengers of humanity, carrying fragments of who we are into the cosmic ocean. In 1972, Pioneer 10 was launched, the first human-made object to leave the solar system. Fixed on its side was a small metal plaque, engraved with figures of a man and a woman, and a map showing the location of our sun. It was simple, quiet, and profound. A gesture to anyone who might find it. Pioneer was followed by other Voyagers, most famously Voyager 1 and Voyager 2, launched in 1977. Each carried the golden record, a time capsule of images, sounds, greetings, and music, an archive of Earth pressed into a disk of gold. These spacecraft continue to drift beyond the planets. Voyager 2 has already crossed into interstellar space, more than 18 billion kilometers from home, still whispering faint signals to Earth, still carrying our message. They are small compared to the scale of the cosmos, yet they embody something vast, the human desire to explore, to reach outward, to leave a trace. In the quiet of space, they continue their journey, our first true emissaries to the stars, carrying our story farther than we ourselves can go. The mystery is whether these spacecraft will endure. They travel through harsh space, filled with cosmic rays and dust. Their metal may weaken, their electronics may fade. Yet even after more than 40 years, Voyager still speaks, its voice faint but present. Its signals arriving after long hours of travel across the void. Each transmission is like a heartbeat, steady, fragile, a reminder that something human drifts beyond the sun. We imagine the spacecraft as small sails, gliding slowly in the cosmic sea, pushed not by wind but by momentum, drifting toward unknown shores. They may wander for millions of years, silent after their systems fail, yet still carrying their records, their plaques, their traces of Earth, drifting through starlight. Perhaps they will pass near distant suns, unseen and unrecognized. Perhaps one day they will be found, opened, read like forgotten letters. The mystery is not only if they survive, but if they will ever be noticed. The universe is vast and dark, yet still we let them go, hoping their journey has meaning. They are like bottles cast into the ocean, fragile and alone, yet carrying with them the voice of humanity written in metal and gold. Some believe these spacecraft will become the longest lasting artifacts of humanity, long after cities crumble and mountains erode, long after even languages change. The Voyagers will still drift, silent monuments to a species that once reached for the stars. Others argue that they may not last. Cosmic radiation could strip them. Collisions with dust could shatter them. The universe is not empty, but filled with dangers. And even the strongest machines may eventually decay. There is debate over what they truly mean. Are they signs of our wisdom or of our longing? Are they gifts or just debris carried outward? Yet hope persists. If ever they are found, they will carry a story, not of power but of curiosity, not of conquest but of connection. They would tell that on one small planet beings once looked up, wondered, and chose to send a part of themselves outward. If another intelligence one day finds them, they will see that humanity once existed, fragile and thoughtful, willing to share music, greeting, and images of our world. In that way, the spacecraft are not only machines, they are voices. And the question remains, what will they say about us when they are heard? Radio signals have been leaving Earth for more than a century. Invisible waves spreading outward at the speed of light. They carry voices, music, and images of our world. When the first television broadcasts lit the air, they also began a journey into the cosmos. Episodes of early shows like I Love Lucy from the 1950s are now more than 70 light-years away, rippling gently through the stars. These signals are unintentional messengers, not crafted for alien ears, yet they still represent us, echoes of human laughter, songs, and words traveling far from home. Scientists describe them as a growing bubble of sound and light, a sphere now about 200 light-years wide, surrounding our planet, expanding with each passing year. Within that bubble, thousands of stars rest, perhaps with planets, perhaps with listeners. Whether or not anyone can hear them, the signals exist, stretching across the dark, faint but persistent, carrying fragments of Earth. They are not golden records or plaques carefully prepared. They are ordinary broadcasts, daily life transformed into cosmic whispers, and together they form the first true voice of Earth, speaking not in one language, but in the shared rhythm of radio waves. The mystery is whether those signals are strong enough to be heard. Space is not silent, but full of interference, radiation, and distance. And as the waves travel farther, they fade, becoming weaker with every light year. Would another civilization have instruments sensitive enough to catch them? Or would they dissolve into the cosmic noise? The search for such voices has been mirrored here on Earth. Through projects like SETI, scientists have listened to the sky, hoping for an artificial signal, a message from someone else. None has been confirmed. The sky remains quiet, Yet still we send, not deliberately but continuously. Each broadcast of radio, television, and radar joining the chorus, it is like a song carried into the night, sung softly across a vast stage, a melody no one may hear, yet still sung. These signals are like the breath of earth, exhaled without intent, yet filled with character. Each wave a signature of human presence. Even if no one listens, the signals are real, flowing outward like ripples across water, a trail of our existence written in invisible lines of energy, fragile, fleeting, yet undeniable. Some suggest that radio signals could one day be intercepted, perhaps by a civilization more advanced, perhaps by neighbors we have not yet imagined. If so, these signals would become the first contact, an unplanned introduction. Others argue the waves will fade long before they reach anyone, that the distances are too vast, that the universe is too full of noise, and that no one will ever hear them. There is debate about what they reveal. Some say they are careless, broadcasting wars, advertisements, and noise. Others say they are precious, revealing the vitality of human culture. In either case, they are out there, continuing to spread, a vast bubble of information that cannot be taken back. If one day another intelligence does hear them, what would they think? Would they understand the laughter, the songs, the dramas, or would it all dissolve into static? Perhaps they would hear the pulse of a species still young, still searching, still alive. Perhaps they would know that somewhere in the galaxy there was once a world filled with voices, carried on invisible waves, drifting like light across the deep sea of space. Not all of humanity's messages are deliberate. Some are written in the very air of our planet. The atmosphere of Earth is changing, and from space it can be measured, traced, and recognized. Human industry, agriculture, and energy use have altered the balance of gases, increasing levels of carbon dioxide, methane, and other compounds. These changes are visible from satellites orbiting above. The Sentinel-5P satellite, for example, has mapped methane plumes, trails of invisible gas rising into the sky. Others have measured rising carbon dioxide linked to factories, cars, and fires. Today, the concentration of carbon dioxide is higher than at any point in the last 800,000 years, a fact etched into ice cores and confirmed by modern instruments. From orbit, Earth's breath is not the same as it once was, its chemical fingerprint altered by human activity. Some scientists suggest that such changes might be visible even to distant observers, that an alien astronomer studying Earth could see unusual gases in the spectrum of our atmosphere, markers of technology and industry. In this way, the air itself becomes a message, unintentional but real, a sign that life here has not only grown but changed the planet itself. The mystery is whether these atmospheric fingerprints would be understood as signs of life. From afar, a planet's atmosphere is seen through the faint absorption of starlight, its gases revealed as tiny patterns in the spectrum. Would another observer recognize carbon dioxide and methane as signs of technology? Or would they mistake them for natural processes? From Earth, we already use this method to study exoplanets, searching for water vapor, oxygen, or other possible indicators of habitability. In the same way, another intelligence could see Earth as unusual. Our atmosphere is like a breath, slow and continuous, yet now altered. Its rhythm changed by human hands. Satellites trace this breath, showing how forests burn, cities expand, and industries grow, each a line in the air above us. It is like a pulse recorded on a cosmic chart, fragile but persistent, revealing our presence not in words or music, but in chemistry. The question lingers. Would such a trace be enough? Would another civilization see it as evidence of life? Or would it fade unnoticed? Another chemical variation among countless worlds. Some scientists argue that changes in Earth's atmosphere are a strong marker of civilization, a techno-signature that might one day allow distant astronomers to detect us. Others caution that it may not be so clear. Natural processes can also produce gases like methane, and interpreting signals across light years is uncertain. There is debate not only about what can be seen, but also about what it means. Does an altered atmosphere represent progress or warning? Does it show intelligence or imbalance? To us, it is both a signature and a mirror, telling the story of how human activity reshaped the very air we breathe. If another intelligence were to read this story, what would they think? Would they see resilience and growth? Or would they see recklessness? Perhaps in the future, the atmosphere will change again. Perhaps it will stabilize. Perhaps it will carry new markers of cleaner technologies. Whatever happens, it will remain our footprint, written into the sky above us. The atmosphere is our silent letter, drifting upward with every breath, carrying the record of our civilization, fragile, undeniable, and still unfolding. The vision of space colonization has long captured human imagination, once confined to the pages of science fiction and now increasingly grounded in science. The Moon and Mars stand as our nearest candidates, worlds within reach, yet still carrying immense challenges. NASA's Artemis program, scheduled to return humans to the Moon by 2028, aims not only to plant flags and footprints, but to establish a sustainable presence, one that can serve as a gateway to deeper space. Mars, with its vast reserves of frozen water beneath the surface, offers tantalizing potential. Water means life, fuel, and the chance to create self-sustaining habitats. Studies of closed-loop ecosystems suggest that humans could recycle air, water, and even grow food far from Earth. The International Space Station has already demonstrated our capacity to adapt, even in the fragile environment of orbit. What once seemed fantasy now shimmers as possibility. Villages of light nestled against the darkness of alien horizons, where human voices echo for the first time beyond Earth. Yet mysteries surround the dream of long-term survival beyond Earth. Can human bodies truly endure decades in reduced gravity, or centuries under alien skies? The ISS has given us glimpses: muscle loss, bone thinning, changes in the human heart. Mars would add radiation storms, dust-filled air, and the cold silence of distance. Some scientists wonder whether humanity will remain biologically the same after generations lived elsewhere. Will colonies become variations of humanity, adapted uniquely to their new homes? And then there is the question of spirit. How will it feel to raise children beneath a pale blue sun on Mars, or within domes pressed against the vacuum of space? Colonies are often imagined as shining villages scattered in the sea of stars, lanterns of human resilience. But the unknown stretches far ahead, and each answer seems to bring deeper questions. The first steps will be fragile, uncertain, perhaps filled with failure. But every stone laid on alien ground would mark humanity's attempt to leave Earth's cradle and embrace the universe. The hypothesis that colonization could secure humanity's survival is both inspiring and troubling. If Earth suffers catastrophe, nuclear war, asteroid impact, or climate collapse, colonies on the Moon or Mars may serve as life rafts. This vision paints colonization as humanity's insurance policy, ensuring our story continues even if home is lost. Yet there are debates that weigh heavily. What if, in reaching new worlds, we repeat old mistakes? Would the exploitation of Martian soil mirror the industries that scarred Earth? Some scientists argue that terraforming another planet could erase ecosystems we do not yet understand. Even if microscopic, the ethical question echoes: do we have the right to transform other worlds simply because we can? And then, what would we choose to carry from Earth? Culture, memory, seeds of forests, archives of music and art. Colonization asks not only whether we can survive, but who we wish to become when we do. The debate remains unresolved, stretching between hope and caution. Still, in the silent deserts of Mars, the idea lingers: a place where the echoes of Earth may find a new beginning. Technology has always been humanity's lantern in the dark, illuminating corners of the universe that once seemed unreachable. Telescopes, probes, and artificial intelligence are now extending our vision across time and space. The James Webb Space Telescope, launched in 2022, has already unveiled galaxies more than 13 billion light-years away, offering glimpses into the dawn of cosmic history. Robotic explorers like Voyager, Perseverance, and New Horizons act as our mechanical scouts, carrying instruments that record, photograph, and analyze worlds on our behalf. AI-driven algorithms sift through endless streams of data, identifying exoplanets orbiting distant stars, over 5,000 of which have already been confirmed. Each discovery stretches the map of the known cosmos a little farther, marking not just locations but possibilities. These machines, born of Earth's ingenuity, are our extended senses, traveling where human bodies cannot yet follow. In their images and signals, humanity finds its reflection curious, restless, and unafraid to ask the universe for answers. But questions remain. Will technology ever be enough to bridge the gulf between knowing and truly understanding? Our probes sample Martian soil in search of ancient microbes, while our telescopes analyze exoplanet atmospheres for hints of water and oxygen. Still, the silence of the cosmos lingers, as if holding back its secrets. The Perseverance rover, wandering across the dusty plains of Jezero Crater, carries tools built to detect chemical traces of life billions of years old. Yet even if such traces exist, they may whisper too faintly for us to hear. Technology is like a torch flickering in the vast cavern of the universe, bright enough to reveal shapes, but not always the meaning behind them. For now, we continue to listen, scan, and calculate, chasing shadows that may someday resolve into clarity. Each breakthrough feels like the lifting of a veil, yet beyond it lies another curtain. The universe seems to invite us forward, step by careful step, as if testing both our patience and our humility. Many scientists hypothesize that within the next few decades, technology may uncover undeniable evidence of extraterrestrial life. Perhaps it will be microbial fossils on Mars, biosignatures in the clouds of Venus, or chemical patterns in the light of distant exoplanets. Others caution that life, if it exists, could be so alien that our instruments may fail to recognize it. The debate widens. What if we find signs of intelligence radio waves, artifacts, or even ruins? Are we prepared for such a revelation? And conversely, what if we search for centuries and find nothing? A silence that redefines our sense of uniqueness. Technology carries the power to answer, but also to confront us with truths we may not be ready to accept. Some argue that even the act of searching changes us, reminding us of our fragility and our hunger to belong to something larger. In every debate, one idea returns. Whether we find life or not, the journey of exploration itself becomes part of humanity's legacy, etched into the record of the cosmos as proof that we looked up and dared to ask. While spacecraft and technology represent our physical reach, culture represents the soul we send into the cosmos. In 1977, the Voyager probes carried the famous Golden Records phonograph discs etched with sounds, images, and greetings in 55 languages, along with music ranging from Bach to Chuck Berry. These were not scientific tools, but time capsules, meant to embody the essence of humanity should they be discovered by another civilization. Messages like these reveal a different kind of ambition, to be remembered not only as explorers but as storytellers. Radio transmissions, such as the Arecibo message of 1974, carried mathematical symbols and diagrams intended to demonstrate intelligence across the stars. Art, music, and language have thus become woven into our exploration, reminding us that discovery is not just about what we find, but also about what we choose to share. Culture becomes a mirror held up to the cosmos, saying, "This is who we are. This is what we hoped to preserve." Yet mysteries follow. If another civilization were to stumble upon these cultural artifacts, would they understand them? A Beethoven symphony might stir universal emotions, or it might be heard as meaningless vibration. Mathematical patterns may seem precise, yet even numbers are interpreted through context. The Golden Record drifts silently in the interstellar dark, like a sealed letter addressed to an unknown recipient. Will it ever be opened? And if so, what story will it tell? Even the act of sending art into the cosmos transforms it, turning music, words, and images into signals of longing, of a species reaching beyond its solitude. Each broadcast is like a candle flickering in the night, uncertain if anyone will ever see its flame. Still, there is a quiet beauty in the attempt, as if humanity is whispering across the void. We are here. We existed. We dreamed. Some hypothesize that cultural transmission may be our most enduring legacy, even outlasting our species itself. Long after Earth changes or civilizations fade, the Voyager. Golden records could still be traveling among the stars, carrying echoes of human laughter, music, and thought. Advocates believe this could form a bridge to other intelligent beings, a gesture of goodwill across incomprehensible distances. But critics argue, what if our culture is misunderstood? Or worse, dismissed as trivial? Could we even risk attracting attention we may not survive? The debate continues, balancing pride with caution. Beyond speculation lies a deeper question. If we are to be remembered, what part of ourselves do we wish to leave behind? Violence and conflict, or compassion and creativity? The cultural artifacts we cast into space are not just for others, they are messages to ourselves. Reminders that even in our brief passage through time, we sought to leave beauty in the darkness. And perhaps that effort alone ensures we are never truly forgotten. As we drift into the conclusion of our journey through the stars, we return to the present moment, our fragile world, and our fleeting time in the cosmos. The universe tells us stories of stars, galaxies, black holes, and the pale blue dot on which we live. All of these remind us that we are both tiny and unique. The thin veil of Earth's atmosphere glows as a signature that can be seen across light years, a delicate sign of life and civilization. Every action we take leaves a ripple that stretches outward, a faint radio call, a spacecraft silently gliding into interstellar space. Even the slow work of colonization one day will be a mark on the cosmic canvas. Our presence is written in these traces. Do we see how extraordinary this is? Do we feel the weight of being small yet leaving a mark so vast? The footprints of humanity already shine into the universe. Our oldest radio signals keep traveling. Voyager carries the golden record with whispers of who we are. Yet the rising carbon dioxide in the air is another message, one less harmonious. Both are truths. Both are parts of our inheritance, like stars that recycle dust into new generations. We too shape what comes after us. Our choices build legacies. What kind of footprint do we want to leave? A gift to the stars, a warning, or a quiet poem written in light? Could we imagine that the universe is listening as gently as we are listening now? When we step back, the universe offers no judgment, only the vast invitation to wonder. It has lasted for 13.8 billion years, while our story is a brief flicker, a momentary flame seen against endless night. Yet within this instant, we are explorers. We are guardians. We are wanderers passing through. The stars ask us to reflect on this role softly and kindly. They remind us that every heartbeat is part of the cosmic rhythm. We may ask, are we guests? Are we builders? Are we dreamers? Perhaps we are all of these. The universe does not rush us. It simply holds space for our questions. Imagine far into the future. Our descendants may look back at this time and see the fragile beginning of a species reaching for the stars. They may ask, who were they? What dreams did they carry? What story did they leave in the fabric of the universe? And as you rest now, you carry these questions too. Let sleep guide you, like a gentle current drifting among constellations. Take with you the rhythm of the cosmos, the breath of galaxies, the whisper of time. Let the thought settle softly. You are part of the great story of the universe, and tonight, as dreams rise, you are exactly where you belong. If you wish to continue listening to gentle stories of the cosmos and finding peace in its endless rhythm, we invite you to subscribe to Cosmic Sleep Science. Each night you can return to the quiet embrace of the universe, learning relaxing facts that guide you into rest. Let this channel be your doorway to wonder and to sleep, a soft place where science becomes a lullaby and the cosmos sings you home.